Hello atmospheric science students, Dr. Shragi here, and I am giving you lecture 24 in the boundary layer meteorology class. I'm actually having all kinds of trouble with recording today, so the best I could do was be outside here, where, it's a long story as to why that has to be, and I've actually got the presentation here on my phone, and I'm just kind of showing you what you're probably seeing behind me on this YouTube video. Several times in this this module of the course, when we've been talking about boundary layer meteorology, we've seen diagrams that look like this one, where we're kind of showing the evolution of the boundary layer over the course of a 24-hour period. Time is on the x-axis, and height is going to be on the y-axis. This particular one, which came from page 73 in the Stoll textbook, is a bit of a complicated mess because it also has profiles of potential temperature and so on. But really the only thing I'm interested in on this particular figure is how this set of curves that show how the height of the boundary layer is evolving with respect to height. So, with respect to time rather. So I've got sunset labeled there with kind of a black line, and I'm sorry, sunrise labeled there with a black line, and sunset labeled there with a red line. And the main thing I want you to notice is that sort of red and black dashed line I've got on there that is indicating Zi, the height of the top of the boundary layer. And we're interested in partial Zi, partial T, which would be the evolution of the height of the boundary layer with respect to time. Now for the first few hours of each day, the height of the boundary layer is growing. Partial Zi, partial T is positive, but the rate of growth is fairly slow, and so we get this, very gentle growth with respect to time and the height of the boundary layer. But a few hours later, we're going to see that the boundary layer is growing very rapidly. Late morning, early afternoon, we're going to see that the boundary layer height is increasing very rapidly with respect to time. Partial Zi, partial T is not only positive, but large. Yet late in the afternoon and in the early evening, just in those last few hours before sunset, the rate of the boundary layer's growth goes very, very slow again. Again, it's not negative, it's still growing, but very, very slowly with respect to time. And so, I guess the question I would be asking you is why? Why is the growth of the boundary layer this way? What causes the boundary layer to have different growth rates with respect to time? And to understand this, we need to get back to our idea of entrainment. The boundary layer grows by entrainment of mass from the free atmosphere down into the boundary layer. I was thinking about this before I made this video, and I was thinking, students could have other ways that they might think that this would work. For example, a student might be forgiven for thinking that it is done by for example, maybe the boundary layer warms with respect to time, and that would be expanding it. No, that's not what it is at all. It's literally the entrainment of mass into the boundary layer. Now, if you're not comfortable with the whole business of entrainment, please get a hold of me with that with some questions, okay? I have resources that we use in intro or whatever. I mean, we're not going just too far into entrainment here. The basic idea here is that you're just talking about air parcels mixing with their environment. But if you're uncomfortable with that, please let me know and I can get some resources for you. Now, what I'm going to be doing here on this slide is I'm actually illustrating for you we're going to build a profile of the boundary layer in the free atmosphere here. I'm doing this during the day, so most of the depth of my boundary layer is being illustrated here as a statically neutral mixed layer. It's neutral because of all that mixing. And then there's going to be a radix layer in the lowest, maybe 20 meters or something below there, where it's going to be statically unstable, absolutely unstable, so we can get these buoyant air parcels rising and so on out of the radix layer. Then we're going to have Zi, the top of the boundary layer. And from there on up, it's the free atmosphere. It's going to be pretty statically stable, at least conditionally stable, if not absolutely stable, is the typical situation in the free atmosphere. And those lowest few meters of the free atmosphere are going to be the entrainment zone, and that's going to be extremely stable. Okay, we don't yet know exactly how far we're going to say that is as far as how many meters thick that layer is, the entrainment zone or whatever, capping inversion or whatever you want to say. But we're going to say that is statically stable, very statically stable. So let's start with an air parcel down here near the surface of the Earth, and we're going to say that's going to start to rise. I don't particularly care why this air parcel is rising. Maybe it had to flow over a hill. Maybe there was some low-level convergence and there was no place for the air parcel to go but up, whatever. For some reason, an air parcel started to rise. It might even just be something as simple as buoyancy. That air parcel was warmer than the air around it. Maybe it was over an asphalt parking lot. I don't care. For some reason, this air parcel started to rise. But down there in the radix layer, because it is absolutely unstable, that is to say the potential temperature is decreasing with respect to height in the environment, Well, this air parcel is going to rise, and it's going to accelerate upward. Once that air parcel has started to rise, it is warmer than the air around it. It'll experience a positive buoyancy force, and it will accelerate upward through that radix layer. Again, we're only talking like maybe 20 meters or something like that, but it's going to accelerate upward and get itself up into the mixed layer. Now in the mixed layer, all that mixing has meant that potential temperature and other conserved quantities are constant with respect to height. It's statically neutral with regard to stability. You'd be forgiven for thinking that means that, like, through the mixed layer, the air parcel that we have lifted from the surface will be neither encouraged nor discouraged to rise. But that's not exactly what's going on here, because remember, this air parcel already is warmer than the air around it, because it started at the surface. It conserved potential temperature while the environment around it cooled for those first 20 meters or so. This air parcel already is warmer than the environment when it got up into the mixed layer. So that air parcel is experiencing a positive buoyancy. It's continuing to accelerate upward through the depth of the mixed layer. Now, as it rises up along the way, it probably will hit some kind of lifted condensation level. It might not. It might not hit the lifted condensation level if, like, the dew-point depression at the surface is fairly large. But it probably will hit the lifted condensation level and start forming a cumulus cloud. It might be cumulus humilis or cumulus mediocris or something like that. But at some point, it'll probably have hit the lifted condensation level and continue to rise until it hits Zi, the top of the boundary layer. Okay, so it's going to hit the top of the boundary layer. Now, the entrainment zone, which is what's right above there, is extremely stable. Any air parcel that is lifted up into the entrainment zone is going to want to lower back down, return to its original altitude. But keep in mind, our air parcel that was rising from the surface and became this cumulus cloud, it punches through Zi at some velocity W, U in the north-south direction, V in the east-west direction, and W in the vertical direction. And so even though there's a negative buoyant force, once that air parcel punches through Zi and is up in the entrainment zone, yeah, there's a powerful restoring force of negative buoyancy trying to push that air parcel back to the surface, but it has some momentum upward already due to its vertical velocity W. It's going to take a little while for that air parcel to slow down, reach a velocity of 0, and then start heading back down towards the surface. And, well, the question is how far? How far will that air parcel punch through the capping inversion, or punch through Zi and get up into the entrainment zone? Well, that's sort of the $64,000 question. It kind of depends on how big W is, how strong this updraft is. It depends on how strong the stability is of the entrainment zone. These are kind of questions we'll be asking in a little bit, but right now, let's just say it will turn around. Okay, this air parcel that rose from the surface, hit its lifted condensation level, punched through Zi, will make it a little ways through into the entrainment zone, at least a few, maybe tens of meters or something, before the stability overcomes its vertical motion, and now the air parcel is going to start, it's now cooler than the environment, and it's going to start accelerating downward. Okay, this is the restoring force here that is accelerating this air parcel downward back towards the surface. Once it goes back down through the height of the top of the boundary layer, Zi, it'll be back down into the mixed layer again, and now again the mixed layer, it's well mixed, it's statically neutral, it's not exactly resisting the vertical motions that are at work on this air parcel, and as a consequence, this air parcel will, it'll have accelerated downward through the entrainment zone, and then it'll be sinking through the depth of the mixed layer, and then finally it'll probably actually reach all the way down to the surface. And so your air parcel that started at the surface and rose to Zi and may actually punch through a little bit into the entrainment zone will now have sunk back down to the surface and to finish this circulation. This, by the way, is how gusts of wind happen, for example. That air parcel that lifted up to the top of the entrainment zone, when there was some entrainment going on up there, it also mixed in some of the higher momentum of the air that was up there in the free atmosphere and it brought it down. That's a gust of wind. Okay, so on slide 19 then, at every step of the way, there's been entrainment going on. I mean, there's no real idea. Air parcels are kind of a silly idea when you think about it. They're not really separate from the environment. At every step of the way, there's been mixing motions that have been mixing environmental air into the air parcel. But the issue is, when that air parcel was down in the mixed layer, it wasn't really all that different from the air in the mixed layer. All that air down there in the boundary layer, in the mixed layer, was air that had recently been at the surface too. The temperature wasn't all that different. The moisture wasn't all that different. You know, whatever entrainment was happening to our air parcel as it was rising through the mixed layer didn't really hurt much of anything. But we can't say the same to be true of what happened once the air parcel punched through Zi and it was up into the entrainment zone. So let's take a closer look up there as to what's going on once we're above Zi. So if I kind of zoom in on this figure here, see now we have air parcel that came from down by the surface surrounded by an environment that's in the free atmosphere. And what's going to happen here? Well, entrainment's going to happen, and we're entraining two very different volumes of air. The potential temperature, and actually the air temperature of the air parcel coming from the surface is much cooler than the environmental air up there in the entrainment zone, because it's, you know, absolutely stable. They're in a temperature inversion. The free atmosphere is drier. There's all kinds of differences here. Let's focus, though, on the temperature for a moment. If we take that environmental air in the entrainment zone that's warm, and we combine it with some colder air that came, you know, that was lifted from the surface, has been cooling dry adiabatically and so on, you're going to get it mixed. When you mix those together, you're going to get air that is colder than the environment, right? You take environmental air, you add cold air to it, you're going to get air that is colder than the environment. So this air parcel is going to sink, no questions about that. Mixing with the air that is in the entrainment zone doesn't result in an air parcel that's going to keep rising, it results in an air parcel that's going to sink back down where it came from. And it's going to have added in this mass that it entrained into it from the free atmosphere. 1 unit of air, let's say, will have risen through Zi from the boundary layer, but like 1.1 units of air will sink back down through Zi into the boundary layer, because we have brought in some air by entrainment. We have entrained some air. Therefore, there is a flux of mass from the free atmosphere down into the boundary layer across Zi, where we have a net transport. There's some transport of air up through the Zi, there's some transport of air down through Zi, but the down is more than the up. There's a net flux of air. A flux. Let's talk about fluxes again. A flux is stuff moving through a square meter per second. In this case, the stuff is a volume of air with units of like cubic meters. A square meter of like the top of the boundary layer. Here is a square meter of the top of the boundary layer, and so many cubic meters of air are passing through it per second. We'll work through those units. Cubic meters per square meter per second works out to meters per second. That's kind of an amazing thing. This flux, this transport of mass from the free atmosphere down into the boundary layer has units of velocity, meters per second, and it has a very, very important, it's an important velocity in atmospheric sciences. It's called the entrainment velocity, and its symbol is WE. W because it's a vertical motion component, E because of entrainment. The entrainment velocity, oh man, students always want to hook a bad idea onto this. They want to say, oh, the entrainment velocity is the velocity of the air that's entraining. No. The entrainment velocity is how fast the entrainment is happening. No. Nothing is moving at the entrainment velocity. That's not the point here. It's the units are a unit of velocity, but it is a flux. It is a transport of material from above the boundary layer into the boundary layer. So we have some height Zi. We're on slide 24 here. If we have some height Zi and mass is moving through that level Zi down into the boundary layer, there's nothing that Zi can do except get higher. So as we have entrainment across the entrainment zone, the top of the boundary layer can only grow. We can only get growth of the boundary layer. Can you hear the trains in the background? We can only get growth of the boundary layer. Well, maybe. See, there's actually a couple of different processes here at work. There's actually a slide missing from the presentation, but I can't fix that right this second here. We only really care about the growth of the boundary layer under conditions where there is a fair weather. anticyclones, large-scale sinking motions, or whatever. We don't worry about boundary layer meteorology really under like stormy conditions and cyclones and so on. That's not really when boundary layer effects aren't as big as the effects of like fronts or frontogenesis or something like that. Well, under the kinds of conditions in which we are worried about the boundary layer, yes, the boundary layer is growing by the effects of entrainment from above, but it's also being smashed or squished or something by the large-scale anticyclone. The large-scale anticyclone that it's part of has large-scale sinking motions, which I'm illustrating on this slide, what are we on here, 25, with this down arrow that's sort of over the whole thing. There's large-scale sinking motion going on in an anticyclone that is forcing everything down, including ZI. That layer of air between ZI and the surface is just getting squished, and in fact it'll have surface divergence away. It's an anticyclone. So see how there's two different competing processes affecting partial ZI, partial T? There is a change in the height of it that's due to entrainment, that's forcing it to grow, and there's a change that is due to the large-scale sinking motion associated with the anticyclone. We denote that large-scale sinking motion as WS. W because it's a vertical motion, S because it's synoptic scale. Well, WS is actually not really something, that's not really a topic we can address in this class. That's a synoptic meteorology thing. We would have to have the knowledge that we gain in a class like synoptics to understand what the speed of the sinking motion is that is gradually forcing ZI down. Well, what are the factors that are affecting, making WE increase? Hey, phone, wake up. This is not working as well as I'd hoped. Alright, hold on. There we go. Alright, well, I got this equation from the Stoll textbook here, where WE is approximately equal to A times FH at the surface, all divided by delta theta. This is an equation that describes then the entrainment velocity. The synoptic scale WS, that is about the substance associated with the anticyclone, I can't tell you what that's going to be. That's a synoptic thing. You have to figure out things about the strength of this anticyclone. That's not a boundary layer thing. Alright, what are the terms that go in this WE, this entrainment velocity as Stoll has it expressed in here? Well, one of them is A. Now this A is a number called the Ball ratio, and the Ball ratio is actually a rather sophisticated topic in a boundary layer meteorology class. If this was a graduate boundary layer meteorology class, we'd have like lectures about how to compute the Ball ratio. For our purposes, in this kind of application that we're talking about right now, a good typical value of the Ball ratio is A equals 0.2. Okay, let's just use that as our value of the Ball ratio, not worrying about what it is. We're just going to pretend it's a constant or something like that. FH at the surface. FH is the flux of heat at the surface from the surface into the atmosphere. For the purposes of what we're doing in this class, you can think of that as conduction from the warm ground into the atmosphere. It's a little more complicated than that. It also includes certain kinds of radiative effects. It also includes certain kind of turbulent processes that happen extremely close to the ground. But for our purposes, it's sufficient to think of it as conduction from the warm ground into the cold, relatively cold air above the ground. That will help solve our problem here. The mysterious term in some ways here is this delta theta. What's going on with delta theta? This delta theta term in the definition of the entrainment velocity is a term that is known as the strength of the capping inversion. And what I did here on slide 29 here is I've actually stolen a figure out of the Stoll textbook. I think it comes from page 75. And for the purposes of this figure, let's only even worry about the left panel. This left panel, Stoll's trying to illustrate for you a fairly typical looking potential temperature profile in the boundary layer during the day. And he's using that dashed line to illustrate this. And you can see all the good stuff we already know about potential temperature profiles in this diagram here. For example, you can see that the potential temperature profile is roughly constant with respect to height in the mixed layer. You can see the absolutely unstable radix layer there. You can see how there's a big inversion right there at the top of the boundary layer, and then change in potential temperature with respect to height is positive but small through the rest of the depth of the free atmosphere. All the good stuff we know is out there. And what Stoll says here is, for teaching purposes, let's just say let's say we can approximate this by this sort of dark, the solid line that's on there, which is just going to be like a little simplified version of the potential temperature profile, where we're just going to say, hey, the potential temperature is constant through the boundary layer, It gently increases with respect to height in the free atmosphere, and there's sort of a little corner there, or a little jog in the curve right there at the top of the boundary layer. And that little jog, if you will, is what is the value of delta theta. Delta theta here is like the difference in the potential temperature. See, here's the deal. The potential temperature is lower in the mixed layer, and the potential temperature is higher in the free atmosphere. And the area right between them, that little capping inversion, or that little entrainment zone, it isn't very big. So just that little delta theta is just the difference between, it's that little jump in theta as you go from the mixed layer up into the free atmosphere. Stoll tries to define it in his textbook as saying that it is the potential temperature just above Zi from minus the potential temperature just below Zi. That can be a way to make it work. It's a little bit awkward. But the basic idea here is that the stronger the capping inversion is, that is, the more stable your entrainment zone is, the bigger the value of your delta theta is going to be. And so, now that we are armed with our understanding of what these terms are, we can look back and say what they mean for WE. WE, then, well, let's see, for example, FH at the surface is in the numerator of the fraction here. So the bigger the flux of heat at the surface is, the bigger the entrainment velocity is. Why would that be? Oh, touched the wrong thing there, sorry. Well, the more you have a flux of heat from the surface into the atmosphere, the more thermals you're producing. And every thermal that you produce, and it rises through the boundary layer and punches through Zi and gets up there into the entrainment zone, each one that has that happen has a chance to take a little nibble out of the free atmosphere and bring that mass down to the boundary layer, making a Zi increase. So the more of those thermals you get, the more you are bringing mass down from the free atmosphere into the boundary layer, the more of a flux of mass there is from the free atmosphere down into the boundary layer. In other words, the faster, the greater Fe is, the entrainment velocity. What about the other term, delta theta? Delta theta is in the denominator of the fraction, so the bigger delta theta gets, the smaller the entrainment velocity is. Well, this is the strength of the capping inversion. Every thermal that goes up into the upper boundary layer punches through Zi and gets up there into the entrainment zone. Well, how long it's going to be able to hang out in that entrainment zone before the stability forces it down back into the boundary layer is about the stability of the boundary layer, of the entrainment zone. So, if your entrainment zone is really, really stable, those air parcels are just barely going to punch through, and then they're going to turn around and come right back down into the boundary layer. If the entrainment zone isn't really all that stable, if delta theta really isn't all that big, those air parcels might be able to punch way through the boundary, the top of the boundary layer, and slowly turn around and return to the boundary layer. And all that time that they hang out above Zi is an opportunity for more mass to entrain into them. So, the weaker the cap of the boundary layer is, the more mass can entrain across it. So this kind of steers us back to the answers to the questions we posed right at the very beginning of the lecture. Why was there different growths of the boundary layer at different times of the day? Well, if we look back to like our first one where we saw like in the morning, well, in the morning the growth of the boundary layer isn't very fast because WE is small. And WE is small because of FH. FH is the flux of heat from the surface of the Earth into the atmosphere by conduction. Well, first thing in the morning, right after the sun comes up, the ground really isn't all that much warmer than the atmosphere. There really isn't much flux of heat from the boundary layer, from the surface into the air, so there really isn't much production of thermals. Each thermal that does rise, every plume that rises up and punches through the value of Zi right now, does pull a little bit of air from the entrainment zone back down into the boundary layer, but there just aren't that many of them. So the rate of the growth of the boundary layer just isn't all that great. Meanwhile, later in the day, like late morning, early afternoon, etc., now the sun is high in the sky, it's been beating on the ground for a long time, the ground is really warm. The air temperature hasn't increased that much yet, and so there's a relatively large difference between the temperature of the ground and the temperature of the air touching the ground. Therefore, by conduction, there's a relatively large flux of heat from the surface into the atmosphere. Well, the entrainment velocity has flux of heat at the surface in its numerator. So the the more we warm up the ground, the bigger the temperature difference is between the ground and the air touching the ground, the more thermals we get, the more thermal plumes we get, the more chances there are each of those plumes has to punch through ZI and grab some, entrain some air from the entrainment zone and bring it down into the atmosphere, into the boundary layer. Therefore, ZI increases very rapidly in the middle of the day. And finally, late in the day, we get a situation in which, yeah, the boundary layer is not really growing all that fast anymore in that last hour or two right before sunset. Why would that be? Well, it has to do with the fact that now, late in the day, the difference between the temperature of the ground and the temperature of the atmosphere isn't all that great. The atmosphere has had all day to warm up, and the ground is now, it's directly heated by the sun, and by late in the day, the sun angles are low. The ground's not really warming up anymore. So the temperature difference between the ground and the atmosphere isn't all that great, and so we just don't get much production of thermals during that time, late afternoon. Yeah, if you could produce a thermal, it would rise through a great depth. I mean, the boundary layer's incredibly deep by late afternoon, early evening. But you're not going to get those thermals. So few of them that by that time of day, the boundary layer just isn't growing very much anymore. But all that kind of reflects your experience of what you think the boundary layer looks like when you think of, like, just an ordinary, fair weather day. In the morning, when you first get up, the sky is probably clear. But by mid-morning, you start seeing these cumulus clouds as each individual thermal plume down by the surface is able to rise to its lifted condensation level. In fact, by later in the day, those clouds are getting taller and taller, but by about an hour or two before sunset, there's just not enough heating at the surface anymore. You don't get those thermal plumes very much anymore, and now you're going to have very little production of cumulus clouds, and, that last hour or so before sunset, the skies will be clear again. So this actually gives us lots of explanation of what was going on in that first couple of slides that we saw at the beginning of the lecture. But another really cool thing that this helps us understand is something I talked about a couple lectures ago briefly, and that is the whole business of what kind of screwy things happen to the dew point temperature at the surface right after sunrise. What I have here is a meteogram. I actually have the meteogram here from Omaha this morning. That is actually today. I'm recording this on April 23rd, 2015, and that is the meteogram from Omaha. If you're not familiar with the word meteogram, it's just a graph of meteorological data with respect to time. In this case, this is a 24-hour plot with, times in the past. Farther to the left and farther to the right is the present. And I highlighted on there the time that it corresponds to sunrise on this diagram. In case you're not familiar with how to read them, that's no problem. I just labeled two of the curves on the diagram because they're the only ones we care about for this particular purpose. I put temperature and I put dew point on there, so you can see that the temperature and the dew point are two curves on this diagram here. And if you look, shortly after sunrise, all of a sudden the dew point starts falling. And in fact, if you look at the y-axis of that diagram, it falls a lot. What happened this morning in Omaha that the dew point temperature fell like that after sunrise? Well, now based on this explanation that we've been learning today, I think I can see why. I see how after sunrise we are having some production of thermals as the sun shines on the ground. We start getting these plumes of warm air rising from the surface, each of which punches through ZI, and then we get some dry air from up in the free atmosphere entrained into that air parcel before it comes back down to the surface. Normally we think of the only way to lower the dew point is to make dew, to have condensation, but this actually tells us there's another way. Just mix in some dry air from above. And this works just fine. And so, okay, I could kind of see what's going on here. So after sunrise, as I start growing my boundary layer, I can see how I'm bringing in this dry air from above every time a thermal plume hits ZI, and it's making the dew point rise. And you might be thinking something sounds wrong about this. You might be thinking Dr. Shruggy must be lying to me again. Because Dr. Shruggy, doesn't the boundary layer grow all day long? Yeah. So there's entrainment going across the free atmosphere, across the entrainment zone and across ZI all the time. You're bringing more dry air in all the time. Yeah. Doesn't that mean that the dew point should be falling all day long? I mean, we keep pumping more and more dry air, transporting more and more dry air from the free atmosphere down into the boundary layer. Yeah. Doesn't that mean the dew point should be falling all day long? It would. It would if the only process that was controlling the dew point at the surface was the entrainment of dry air from the free atmosphere. But that's not the only process controlling the dew point. down at the surface of the Earth, where I'm measuring the dew point in this mediogram, the dew point is actually controlled by a number of processes, but principally evaporation. As water, maybe I should be more accurate, say evapotranspiration, as water is also coming through the leaves of plants. But those processes are primarily controlled by things like the temperature of the ground. The warmer the ground gets, the more evaporation you have. The temperature of the air, the warmer the air gets, the more evaporation you have. The wind speed, well, the windier it gets, the more evaporation you get. Well, those things all will happen today, but they don't happen first thing in the morning. It takes time for the ground to get warmer, it takes time for the air to get warmer, and later in the day when you get all those thermals going, that's when you're going to have the gusty winds that are great for evaporation. Yeah, later in the day, you're going to have a great situation here where you're going to be having lots of evaporation off the surface and the dew point's going to increase. But the first hour or two after sunrise? No. The first hour or two after sunrise, it's just too cold and too still at the surface. You're not going to get a lot of evaporation, but you are getting entrainment and dry air from above, so dew point goes down. And this is actually a topic that's all near and dear to my heart, because it's very related to one of the research questions I work on with my team of researchers, with like the University of Cologne and so on. We work with a lot of data that comes from West Africa, and there's a certain type of cloud that I like to study that's down there. That's not hugely relevant to where we're going with this, but I need to know the entrainment velocity for the kinds of studies that we're doing. We don't even measure entrainment velocity in the United States. We certainly aren't going to be measuring it in West Africa. But I'm saying, hey, can't we use this to figure it out? I have, from equipment that's in place down there, really good estimates of evaporation. Heck, earlier in this boundary layer unit, we learned about how that was done. We learned about how you have an instrumented tower or mast, and you have a couple of instruments along the way, and by the difference in the mixing ratio at two different heights, you can figure out the evaporation rate. I got that stuff. I have really good measurements of dew point. We have these instruments that measure the dew point. I think it's every 30 seconds over West Africa at certain agricultural research stations and so on. That's obviously way better than like hourly measurements of dew point. Well, previously I was showing you, hey, we could explain how changes in the dew point were caused by the entrainment of dry air from the free atmosphere. Couldn't we do it the other way around? If I know the changes in dew point and I know the evaporation, couldn't I do it the other way around and solve for the entrainment? Oh yeah, on paper, no problem. I would love to do that. In practice, it isn't working very well. And the reason it doesn't work very well is because for this to work, you have to really know what is the moisture up there in, above ZI, in the free atmosphere. You have to really precisely know the dew point or the mixing ratio or whatever of the air up above the height of ZI. It would work if you had perfect knowledge of that. It would work just lovely, but the trouble is we don't have very good estimates of that. You know, it's West Africa. We don't have like a lot of weather balloons and so on that are actually measuring the dew point. Now, we have instruments like the HAT Pro. You might remember that term from the radiation unit of the course. The HAT Pro, the humidity and temperature profiler. It's like the same set of instruments that would be on a satellite looking down to measure long-wave radiation and get profiles of temperature. They can actually get profiles of humidity the same sort of way. We just did temperature in the third unit. Well, HAT Pro is the same sort of instruments, except it's on a truck. And they can park it at, like, you know, an ag research station or something like that in northern Benin, and we can get, you know, profiles of the moisture, but it turns out that they're not accurate enough. If we don't actually know what the humidity is right above the top of the boundary layer, then there's no way to get this to work out right. But we're still working on figuring out like the error bars and stuff like that, trying to figure out if we can make this still work, or at least find out how good the observations would need to be that we can start figuring out the entrainment velocity based on things like changes of moisture near the surface. That would be really cool. There'd be lots of cool applications for that. Okay, now we only have one more major topic to go, and that's what we're going to be doing the next time we meet, and it's going to be about turbulence and turbulent kinetic energy. How do you actually get flow to store energy in the form of swirls and eddies in the flow, and what produces that energy and what consumes that energy or destroys it, to use the terminology from boundary layer. So we have one more topic to go, and then the last day we'll just be doing reviews and stuff like that. We'll also do some teacher evaluations and things like that in the next couple days. Alright, I hope this worked, and I will get this video out to you guys as soon as possible. Please let me know if you have any questions. This has been Dr. John Schrage.